Hi, my name is Ethan T. Run Han, and I'm from Chemical Engineering. Today, we will be talking about differential equations. What is a differential equation? It is an equation that contains the derivative of an unknown function. The differential equations are classified as ordinary and partial. Today, we will be discussing the ordinary differential equation to get a better grasp of what it is.
Now let's talk about the history of the differential equations. It first came into existence with the invention of calculus by Newton and Leibniz. In 1695, Jacob Bernoulli proposed the Bernoulli differential equation, which was later on simplified by Leibniz the following year. It's an ODE. The ordinary differential equation is an equation that contains only one independent variable and one or more of its derivatives with respect to the variable. The above differential equation example is an ODE since it does not contain any partial derivatives.
Now, let's talk about the types of ODE and the method to solve them. The first one is separable differential equation. A separable differential equation is any equation that can be written in the form. The term separable refers to the fact that the right-hand side of the equation can be separated into a function of x times a function of y. After separating the variables, the solution of the differential equation can be determined easily by integrating both sides of the equation. Number 2 is the homogeneous differential equations. A differential equation containing a homogeneous function is called a homogeneous differential equation. The homogeneous differential equation has the same degree for the variables x, y within the equation. The next step is to reduce the homogeneous ODE to a separable form in order to solve it by integration. To solve a homogeneous differential equation, we make the substitution y equals vx. Further the differentiation of y equals vx, with respect to x we get the equation beside. We can substitute the value of dy dx in the expression beside to get the below expression. By separating the variables x and v, we get the equation below. Then integrating both sides results in the following expression. Lastly, we substitute back the value of v equals y divided by x to obtain the general solution of the homogeneous differential equation. 3 is the exact differential equation. It is an exact differential equation if there exists a function f of two variables x and y having continuous partial derivatives. In simpler words, the differential equation is exact if and only if it satisfies the condition partial q divided by partial x equals partial p divided by partial y. To solve exact differential equation, we need to make sure it's exact by using testing for exactness. Then write the system for two differentials down. Integrate the first equation over the variable x, and then differentiate with respect to y. Substitute the function u xy in the second equation. From the above expression, we get the derivative of the unknown function. Then we can find the function by integrating the last expression, so that the function u xy becomes the equation below. Finally, the general solution of the exact differential equation will be given. Number 4 is non-exact differential equations. If the differential equation is non-exact, it is possible to make it exact by multiplying using a relevant factor, which is known as the integrating factor. It can be found by using the following equation below. After finding the integrating factor, multiply the whole equation with the factor, then continue the solving steps, same as the exact ODE. Number 5 is the first order homogeneous linear differential equation. We can determine if it is a first order homogeneous linear differential equation if it forms the equation beside and Rx equals 0. It is also linear if both the unknown functions y and y prime are linear, whereas px and rx can be any functions of x. Once we know that it is a first order homogeneous linear differential equation, we can solve it using the general equation or the separation method. The general solution is below. Number 6 is the first order non-homogeneous linear differential equation. It is non-homogeneous if x does not equal 0. Then you need to check if the equation is exact. If it is not, we need to make it exact by finding the integrating factor, as below. Then we multiply both sides with fx. Lastly, by integrating both sides, we will get a general solution. Number 7 is the second order homogeneous linear differential equation. To solve an ODE like the one above, differentiate the equation below. Then substitute it into the ODE. Lastly, solve the quadratic equation by factorization or the quadratic formula as below. There are 3 possible types of solutions to the auxiliary equation, each leading to a different form of solution. 1 is the distinct real roots where there are 2 real roots. 2 is the repeated real roots where 2 of the roots are the same. 3 is the complex roots where there are 2 complex numbers. Number 8 is the second order non-homogeneous linear differential equation. It is the sum of the complementary solution yhx of the homogeneous ODE and a particular solution ypx. We can find yhx by finding the general solution of the homogeneous ODE. We need to find yp. There are 3 ways to find it. The basic rule applies when rx is a single term, choose the corresponding yp. Then the modification rule applies when yp corresponds to a solution of the homogeneous ODE. Then multiply the term by x or x squared for double roots. Last, the sum rule applies when rx is the sum of a few terms of left column of the table. Substitute its corresponding yp into the original equation. Number 9 is the nonlinear differential equation. Its equation is as below. If a equals 0 or 1, the equation is linear. Other than that, it is nonlinear. If it is nonlinear, then we need to set ux equals yx power of 1 minus a. After that, we need to differentiate ux. Lastly, we substitute u equals y power of 1 minus a into the u prime equation to solve the equation by finding the integrating factor using linear ODE steps. Picture of ODE. First is the diffusion processes in materials. By using Fick's law of diffusion, we can analyze the diffusion of atoms in solid materials and determine diffusion coefficients. This is the equation below. 2 is phase transformations. Many substances separate, crystallize, or solidify. ODEs can use growth and diffusion to explain phase change dynamics. Phase fractions and microstructures are predicted by these equations. Electrochemical processes. ODEs describe electrolyte, interface change transfer, mass transport, and electrochemical processes. 4 is fracture mechanics. ODEs are employed in fracture mechanics to describe the propagation of cracks in materials. They help determine crack growth rates, providing insights into mechanical behavior and failure of materials. This is the end of my presentation, and thank you.